Computational thinking is more than coding. It's a mindset. It is a problem-solving approach that breaks tasks into logical, manageable steps. In this sense, it mirrors the way humans naturally think when solving puzzles, planning projects, or even cooking. Its key elements are decomposition, which means breaking a complex problem into smaller, simpler parts; pattern recognition, which is about identifying similarities, trends, or repeated sequences; abstraction, which involves focusing on the important details and ignoring irrelevant information; and algorithmic design, in general, which is the process of creating step-by-step instructions to solve a problem. Computational thinking is essential in helping us understand complexity, predict outcomes, and create solutions efficiently. The term was popularized by Janet Wing in 2006, but the logic behind algorithms is a timeless human strategy. We can understand that computational thinking is less about machines and more about training our minds to see structure in chaos, make sense of patterns, and transform information into action. The abacus is one of the earliest tools humans developed for performing calculations. It allowed people to represent numbers physically, making arithmetic operations more tangible and manageable. The first version of the abacus was a simple counting table. People placed small stones, pebbles, or other markers on a flat surface with special markings to keep track of numbers. Over time, the abacus evolved into a more efficient design. It comprised a rectangular frame with rods on which beads were strung. This allowed users to move the beads quickly along the rods, making addition, subtraction, and even multiplication and division much faster than before. The abacus was more than just a counting tool. It was a foundation for human problem solving, showing how breaking down numbers and following systematic steps could simplify complex calculations. Its design influenced later mechanical calculators and eventually the development of modern computers. The Pascaline was a major leap in the history of calculation, representing one of the first mechanical calculators. Invented by Blaise Pascal in the early 17th century, it used a clever system of gears and cogs. When one wheel turned, it automatically moved the next, transferring numbers and results efficiently. It showed that human thought and logic could be translated into mechanical motion. It laid the foundation for automatic computation, a concept central to modern computing. Pascal built the Pascaline to help his father, a tax collector, with complex calculations, which is a reminder that practical problems often inspire technological breakthroughs. Jacquard's loom was a revolutionary weaving machine that transformed not only textiles but also ideas about automation and programming. It operated using punch cards, with each card containing rows of holes representing complex weaving patterns. By feeding different cards into the loom, it could automatically produce new designs without altering the machine's mechanics. The loom was one of the first programmable devices in history, showing that instructions could be encoded separately from hardware. This concept would later inspire early computer programming ideas. Charles Babbage, who designed the analytical engine, explicitly cited Jacquard's punch cards as a model for how to input instructions into a machine. The analytical engine was a visionary design by Charles Babbage, far ahead of its time. Although it was never built, it was conceived as a steam-powered machine capable of reading punch cards to follow instructions, much like a modern computer. Ada Lovelace, Augusta Ada Byron, worked closely with this concept. She wrote detailed programs for the analytical engine. She explained how it could perform complex calculations and even manipulate symbols beyond numbers, hinting at the potential for general-purpose computing. Her notes were later published as the Fundamentals of Computer Programming, earning her recognition as the world's first computer programmer. Ada foresaw that computers would one day create music, graphics, and more, long before such applications existed, demonstrating remarkable foresight and the possibilities of computing. Hermann Hollerith built on Jacquard's punch card concept to develop the tabulating machine, a major step in information processing. The machine combined punched cards with mechanical gears to handle data more efficiently. Each card represented a unit of data. The machine could quickly read, sort, and count this data. Its first major success was the 1890 US Census, which it completed in a fraction of the time manual counting would have required. Hollerith showed that ideas from weaving and early calculators could be transformed into practical tools for managing information. In 1939, John Atanasoff and his assistant Clifford Berry created the Atanasoff-Berry computer, ABC. Unlike earlier machines, the ABC was fully electronic, using about 300 vacuum tubes to perform calculations. The ABC marked a major shift from mechanical and electromechanical devices to electronic computing. It introduced concepts such as binary representation of data and electronic switching, which are still fundamental in modern computers. Although the ABC was not programmable like later computers, it demonstrated that electronic components could vastly increase computational speed, inspiring the development of machines like the ENIAC. Mark I was a massive computer that combined electrical and mechanical components, representing a key step in the evolution of computing. In the 1930s, the US Navy and IBM sponsored the project at Harvard University, led by Howard Aiken, to build this groundbreaking machine. Mark I could perform long and complex calculations automatically, reducing human error and labor. It was over 51 feet long and could perform calculations that previously took teams of human computers days or weeks to complete. Illustrating the power of automated computation, this example shows how computational thinking and engineering ingenuity began scaling from individual tools to collaborative institutional innovation. During World War II, Alan Turing contributed to the invention of Colossus, one of the first programmable electronic computers. Colossus was designed to break the German Enigma code, allowing the Allies to process encrypted messages at unprecedented speed. Colossus helped shorten the war and saved countless lives, highlighting how advances in computing can have profound societal impact. This project also cemented Turing's role as a pioneer of computer science, linking theoretical ideas to practical applications. This is a striking example of how computational thinking was applied under pressure to solve urgent, high-stakes problems. The ENIAC, the first fully electronic computer, was developed by John Mauchly and J. Presper Eckert, completed in 1946. The press famously called it a giant brain. It was formally named the Electronic Numerical Integrator and Computer, and it featured 18,000 vacuum tubes. It was 100 feet long and 10 feet high, and it weighed 30 tons. Programming ENIAC was a labor-intensive task. Operators had to manually rewire the machine for different calculations, showing how far computer interfaces have evolved since then.